Okay, so those test questions are coming in. I've been seeing the emails all day. So again, the deadline is midnight tonight. And because I've spent all that time grading them, we won't have class on Wednesday because there's only so many hours in my day. So we'll have class on Friday. Any questions about that? A very popular decision, apparently. All right. Any questions? Do I have an idea of what?
Of the date of the third exam?
Yeah, it's probably looking at it like a week from Friday, something like that. I'm looking ahead to what material I've yet to teach and what needs to go on that exam. So it's going to be somewhere in that neighborhood, maybe a day or two after. I'm not sure yet.
Do you want a paper copy of this?
If you guys have paper copies, that's great. I love paper.
It'll be next Friday or the Friday?
Say what?
It'll be next Friday or the Friday after?
Not this coming Friday, maybe a week from this Friday, maybe a day or two after that. I'm not sure. I'm looking at the third exam. Anybody else have paper copies they want to hand in? All right. Okay. Anybody else go to the game on Saturday? All right. Never sit in section 35A. It's filled with the strangest people. All right. And that's saying a lot for a OSU football game. Notes right here. We figured out that people sitting 35A are there to get on TV because the camera shows that section all the time. You don't want to be around those people.
36A isn't much better.
Really? Okay. We had people sitting in the aisle in 36A?
It was like a sardine tin.
Yeah. Okay. All right, so today we're going to talk about some aspects related to the molecular weight of polymers and how they are used to try to calculate information regarding how the polymer chains themselves relate to each other. And this refers to both the polymer chains in the melt as well as the polymer chains in solution. And first thing we need to talk about, which is an extension of what we talked about last time, which chain conformation. And we talked last time about the cis and trans aspects of it, so this relates to that because if two atoms are joined by a single carbon bond, then we can get rotation around that bond because it's only a single carbon bond. Can't do that with double bonds. All right, totally impossible. Rotation does not require breaking of that bond in the case of just a single carbon-carbon bond. And as we talked about before, this image shows you the conformation, which refers to the order of atoms or groups in space that arises from rotation of molecules about the single bonds. And so this is possible in this context, and we talk about the effects of this type of behavior on conformation. And we can look at the energy of these different types of conformations and sort of rationalize that. And this image, first off, it's a problem with getting into areas of chemistry. There's 5 names for the same thing. So cis is equal to gauche. So keep that in mind. And what we're looking at here is a variety of conformations of a polyethylene chain, either cis equals gauche or trans conformations. And to make things worse, and we did mention this before as well, this is sort of showing you everything in 3 dimensions. So, this guy is the carbon atom, and these guys out here are all hydrogens. And you also have hydrogens into and out of the plane. All right, there's one down there, which is behind the carbon atom. And so when we talk about cis and trans conformations, we're talking about the relationships of those hydrogen atoms to each other with the intervening carbon. All right. And so in this context, you've got these ghost configurations, and you don't need to obsess too much about this, but you've got ghost configurations, and then you've also got these trans configurations in which they are not on the same side of the carbon. And it's hard to see in 3 dimensions, so I'm not going to try to belabor the point. And on a test question or homework question, we'll still look at 2D, so don't worry so much about that. But just letting you know that these exist in 3 dimensions. And so we have these 3 stable conformations, and we have energies. And again, I'm just going to go ahead and say this equals cis, and this equals cis to make darn sure that you know what we're talking about. And the energy associated with those different molecular conformations should make sense to you in the context of the fact that these guys, the hydrogen atoms, are farther apart from each other. They're not able to bang into each other, all right? And so the energy of that system should be lower, whereas the cis conformations will be higher energy because they do have that potential, since they're on the same side, to be in interatomic conflict with each other, giving the system higher energies. So hopefully that is something that seems logical to you in this context. Rotation energy is the lowest if the atom-atom distances between the hydrogen atoms on adjacent carbons are at a maximum, all right, and the repulsive forces between them are minimized. And remember, these are just protons, all right. There's not a lot of electronegativity, almost none, if we look at induced dipoles associated with them, but they can still, there's still atom cores. They can still bang into each other. So there's not a lot going on there in terms of repulsive forces, but they can't occupy the same space, regardless of what you say about them. And that lowest energy, as stated, is the trans conformation. Okay, and then between the eclipse portion of the and this gets into the three-dimensional aspects of it again, which you don't need to worry about. Intermediate position where one of the hydrogens is between the two hydrogen atoms and that are on the adjacent carbon atom, and this is called the Gauss conformation, which gives you this higher energy, same side configuration. And so that's all well and good, because the energy necessary to make that happen, that transition between one state and the other, is now available. So under normal circumstances, a larger fraction of the bonds are closer to the trans conformation than the Gauss conformation. So sitting here at room temperature, most of the hydrogens in the polyethylene chain will have that lower energy trans conformation. All right, that should make complete and total sense to you at this point. However, if we increase the temperature, okay, and this should also make sense to you, that everything's moving faster, temperature is motion, you have a lot more energy available in that main chain, and so what can happen is we start to randomize the conformations. Gauss conformations approach those of the trans conformation in the system with the higher temperatures. Okay, that makes sense. As it says, selectivity is reduced as temperature increases. Okay, so one more thing about why thermal motion is important when it comes to polymers. Any questions about it? All right, so now we get into some of the mathematics of this, and it's relatively simple. We'll step you through it here, and then we're going to have a homework coming up in which you go through this and compute all these things, and then you should be familiar enough with it that if you see the same type of problems on a test, you can easily come up with answers that are accurate. And so we start off by talking about the number of conformations that are available on a polyethylene chain. And so each carbon-carbon bond is only allowed to be in one of those three. Trans, of course, gauche and minus gauche, it's like one side of the carbon atom versus the other. All right, that's all that really means. In 2 dimensions, you can't draw this, but they're just saying that above or below is gauche versus minus gauche. Don't sweat the fact that those are the 3 conformations, but that is accurate. And if we look at these polymer chains, every one of those carbon atoms then has 3 potential hydrogen conformations around it. Okay, and so if we look down the chain, every single one of them has that same number of conformations. And so we can compute this by using this factorial approach. If there are only 10 carbon-carbon bonds, all right, in the molecule, then the total number of conformations is 3 to the 10th power. All right, so a lot of potential conformations. And so this sort of reflects what we know about polymer chains, how they want to be as random as possible. This gives them a lot of opportunities to be as random as possible. There's so many conformations that a single chain can have that we can know that they can maximize their entropy because there's so much conformational freedom available to these hydrogens. And this is certainly important because as chains move past each other, these individual carbons might transition back and forth between trans and gauche, trans and cis. That got me saying it now. Trans and cis conformations, all those are very likely as these chains bump into each other as mechanical deformation takes place. All right, so it's got the freedom to enable that type of conflict because there's so many conformations available to them. And that's a relatively trivial molecular weight. If we instead have 10,000 carbon-carbon bonds, which is about a 280,000 molecular weight polyethylene, which is reasonable, that certainly exists. We go well above that if we want to. It's a little on the higher end for commercial applications, but it's still reasonable. The total number of conformations is then 3 to the 10,000s, or 10 to the 4,771, which is a very, very large number, not surprisingly. Okay, so this is one of the reasons why we talk about polymer chains as being very flexible, because they have so many conformational states that they can reach, and this gives it that ability to rotate that is associated with the mechanical behavior of these polymer chains in a solid plastic. Okay, so again, when we get down to the molecular level, certain rules apply. We know the bond angle has to be 109.5 degrees. We now know that it's got 3 conformations, which doesn't sound like much on a single atom, but along the entire chain, there's an enormous amount of flexibility built into the system, while still maintaining all the rules that these carbon-hydrogen bonds must have in relationship to each other. Any questions about that? And so this also applies to everything else. This is polyethylene in the simplest case, but it also applies to other polymer chains as well. Okay, and so then we start to get into these different aspects of polymer chains. And as you know from prior discussions, we talked about solubility especially, we have a number of different ways of arranging the single carbon bonded structure in space. And the solvent argument, of course, holds true here. As we have progressively less and less solvent, the same chain will have different overall volumes that can approximate the same total amount of solid in there, but the space between them changes dramatically, either with or without solvent present. And so there's some question of how long is the chain when it has this many conformations. What this really means is how expanded is the chain when it has this many conformations. And there's a couple of ways of looking at it. We'll use 2 extremes to try to illustrate the case. And this is the one that we know the chains absolutely do not like. The distance between the ends equals the chain length if the chain is fully stretched out. All right, so ignore everything and just stretch that chain out until it's absolutely, totally aligned. So if we have a polyethylene with a molecular weight of 3 million, assume all trans conformation. What is the contour length of the chain? We know that the carbon-carbon bond lengths are 1.54 angstroms, and we know that the bond angles themselves are 109.5, so that's all still true. So then we can crank through this whole contour length, all right? And so hopefully when you see this, this is the extreme case number 1. You know that polymer chains have absolutely no interest in being in this configuration because they only have one configuration, all right? So this is a very high energy polyethylene chain because it's only got one. So the entropy is at an absolute minimum, meaning the energy is at an absolute maximum. So we can look at contour lengths just using this issue of geometry. So we're reflecting the angle and getting the vector. Then we know that we have the number of carbon bonds, which is n, times L, where L is that 1.54 angstroms length, times the quantity sign, theta divided by 2, where theta is 109.5. We run through the math there. Keep in mind, we have to think about CH2 in this context to really accurately measure the overall value, so we'll come back to this later on. Times 0.154 times the sign of 109.5 divided by 2, which is 27,000 nanometers. Okay, what is that in microns? Nanometers to microns. Divide by...
Sorry.
Negative 4. We divide by 1,000 nanometers to microns.
2.69.
So it's 27 microns. All right. You can at least see that in the SEM. It's not that long, though. All right. So it's very small in the scheme of things. It's enormous molecular weight, but really not that big in terms of its physical scale. So even if you subject this polymer chain to this extreme condition, it's not visible to the naked eye, assuming you could see an individual chain. And you could If it was a really wide chain, you might be able to see it in the SEM, but in reality, it's still a pretty small object, even with these enormous molecular weights. All right, so hopefully that gives you an idea of scale here. This is a large, very large, high molecular weight polymer chain. It's still not that big in the scheme of things when you stretch it out. The other extreme, so we go from really long to length approaching 0 if the chain is squished in on itself to form a compact ball. And so we keep squishing this down until it gets to a very small condition, and the distance between one segment and another becomes very, very small. And so we can then think of this as the absolute minimum case. And I don't want to go into it too much, but that's the other example of the in-between cases. We have a maximum entropy here, but a minimum chain extension. In most cases, the chain should have a length between these two extreme conditions. And in fact, I think always is probably a better word. Always has a length between these two extreme conditions. You're never going to get to one or the other, assuming normal thermodynamics applies. Okay, so how do we refer to this? And this is a naming system that kind of doesn't make sense when you first look at it, but it is widely accepted. We talked about radius of gyration earlier. This is kind of in the same ballpark as radius of gyration, where we think about the average radius of that coil as it sits in solution or sits in a molten state. In this context, we're not looking at that radius. We're looking at what's called polymer chain end-to-end distance. And this is not the end of one stretched out chain to the other end of that same chain, or in this case, it's not this distance, all right, and that distance constantly changes depending on the conformation of the polymer chain. So what they do instead, they say this is our end-to-end distance. They literally mean the distance between two ends, whether it's in solution or in a melt. What is that distance? And it should make sense that this relates to molecular weight, because as the chain gets longer, the likelihood of R increasing should also improve. All right. Hopefully that makes some sense. So regardless of all this, which is very, very dependent on conditions, we instead focus on the distance between those two ends and use that as a measure of the molecular weight of these polymer chains, specifically in the context of the environment in which it finds itself. And this is often referred to, good or bad, as the root mean statistical average, all right, which means that you take this chain and all of its neighbors and compute R, or figure out R and measure R somewhere or another, and then square all that, sum all that together, and then take the square root of that. That's what RMS means, if you haven't seen that before. All right, so that is this root mean square value for the end-to-end distance in the system. And so the simplest way of doing this, which is totally not realistic, is to consider each chain has n lengths. Each length has some length L, which we've already talked about, 0.154 for polyethylene, joined in a linear sequence with no restrictions on the angles between successive bonds. So we know off the top of our heads that makes no sense at all, but this is just the first approximation at this model. And so we have a bunch of vectors, each of represents the projection of whatever bond you're considering onto some plane. All right, so you take a plane, put it next to this bundle of links, and then you project all the vectors onto that plane. It doesn't really matter where the plane is, you're just projecting that onto this plane, and that's what it looks like in terms of the lengths of those chains. We know that individually they're 0.154, but how they project depends on the angle that they use when they present to that random flat surface. So we consider each length as a vector, and so these vectors will all have very different values based on that projection. And what we can do is, by summing them all up, we get our value of R at the end, because we know what that distance is between those two ends of the chain. And so the end-to-end vector projects that vector R, and it's the summation of all the individual R's. And that's all well and good, but in reality, we still want to get that root mean distance, because that's what we think of as being this important end-to-end distance. This is just this vectorial representation. It's not really the end-to-end distance we're looking for. And so for that, we bring in some different math. And no, I'm not going to ask you to derive anything, so don't worry too much about this. In the end, it's the formulas that matter. But in this context, we think about those two vector values times each other, which might equal the square root of r, and we can think about the individual summations of these different chain components. We can either artificially say one is different from the other and sum those together, or we can say one is it's a copolymer, so each r is different for each component of the copolymer, and this is mathematically equal to this particular formula here, the summation of r bar squared plus 2 times the two individual summations for r sub I and r sub j, and this then works out to a mean end-to-end distance. This root mean square is going to be equal to something even more exotic in this context, because what we do is we take r sub I and r sub j and set that equal to L squared, which is that 0.154 value, times the cosine of all these different angles that are present in the system, and we say that the r negative 2 is equal to the square root of that length. And then we have an overall expression for it, which looks a lot simpler, which is this root mean square distance is equal to NL squared plus 2NL L squared times the two summations of the different angles involved in the system. And so what we then do is consider that each chain joined in a linear sequence with no restrictions on the angles between them again. Okay, so keep that in mind. This is the no bond angle is beyond question here. It's not 109.5. It's everything including that. And then we can then think of the theta ij as being equal to 0, and then for a freely jointed chain we end up with this parameter, which is this r squared to the root mean squared value is equal to n to the 1/2 times L. And there's this other issue of saying that n is equal to the molecular weight of the polymer, so there's a different way of defining it as being this r squared root mean squared distance is equal to 1/2 the molecular weight to the half power, which is also reasonable because with increases in molecular weight, the end-to-end length of the polymer chain increases. And so this makes at least conceptual sense. Again, as the chain gets longer, then that distance between those ends should also itself get longer. All right, so this all works relatively well. Now, real chain, the next step. So we go from the freely jointed chain. It's an ideal chain model. First off, we assume there is no bond-bond restriction. Every bond can freely rotate, and there is no steric hindrance between carbon and other substituents groups such as hydrogen. All right, that's for the freely jointed chain, but the reality is we know that there is an angle, 109.5, that does have restrictions, and we also know that there is steric hindrance. And so this has to do with how chains interact with neighboring chains and how that can also have an influence on the number of conformations that are allowed in these systems. And this is a much nicer cartoon than what I draw before, but it's the one you've seen already, C1, C2, C3, where we fix these guys in space and we say that this C2 to CH bond can rotate as long as it maintains that 109.5 degree angle. All right, so again, these guys are fixed, can't do anything. This one can spin around, and we are constantly maintaining 109.5 as it spins around, giving us that cone. Okay, so this is much closer to reality than what I just showed you before. And so we have that free rotation model. So the r squared, the root mean square distance is then equal to n times L squared, n being the number of carbon-carbon bonds, L being that distance at 0.154, times the quantity 1 minus cosine theta divided by 1 plus cosine theta, and that is the free rotation model. We know that the bond angle is 109.5, so we can simplify this such that r squared equals 2nl squared, or to get the root mean square distance rather than just the distance, we have this parameter in which we take the square root of that, so it's 2n, the quantity 2n to the 1/2 times L. All right, very simple system in which we have this net distance, and that's for free rotation. Instead, we can also think about the freely jointed chain being equal to this n to the 1/2 power times L, which is a difference between what we just looked at and what we're looking at now. All right, different formulas for different conditions. And what you guys need to be responsible for is just knowing how to work with the different formulas and knowing which formula corresponds to which condition. All right, that's all this is about at this point. Okay, and we go beyond that, which looks very similar. This root mean square value is equal to NL times the same quantity we saw before, and we're adding in a new quantity, 1 plus cosine phi divided by the quantity 1 minus cosine phi, and this phi represents the bond angles that exist in the competition or the conflict with the neighboring atoms. All right, and so it'd like to be 109.5 under all circumstances and spin around, but the reality is there are other polymer chains, and so its ability to spin around is restricted. All right, 109.5 is still true, but it can't spin around as freely anymore, and so that gets in the way of the bond angles that are allowed. And so what we do, and again, this is something that you don't need to derive. I will give you this value. We define a value C sub infinity called the characteristic ratio, all right, which is set to be conveniently equal to this mess of cosine thetas and phis, all right. And so this is a parameter that is characteristic of a given polymer in a given solution typically. It can be a melt, but typically we think about this as a solution. So I'll give you a value for C sub infinity for polystyrene that's going to be somewhere between 5 and 10, like 6.8 or 7.4. I'll give you that number. All right, so you don't need to derive this on your own, so don't be too concerned about that. And because we come up with this nice fudge factor, we can then look at this formula being equal to NL squared times that characteristic ratio at C sub infinity. And so then the root mean square end-to-end distance is equal to the value NC sub infinity to the 1/2 times L. So similar to what we saw before, in this case, C again varies from about 5 to 10. And as I said, you'll see values like 6.8, 7.4, 7.2, things like that are very, very normal. And it changes from one polymer to another. Polystyrene is different from PMA. All right, but again, I'll give you this information, so you don't need to compute it. All right. And then another approach to considering this end-to-end distance is called the Cune segments model, which should be kind of familiar because it's kind of like beta Berger vector. There we go. Kind of like Berger vectors in that it takes these different distances and accommodates them in one simplifying step. And so if we have a real polymer chain, which consists of all the individual bonds in black that are shown here, we can instead take the effective value of B, these Cune steps, and use that to approximate the position in space of the polymer chain. So rather than having to deal with all those individual carbon bonds, we end up using these individual steps to say, okay, we get from one point to the other, and that step, which accommodates many different carbons, then allows us to get the end-to-end distance, but with a lot less computation, basically, or a lot less consideration of all the different carbon-carbon bonds. All right, so that sort of makes some sense. It's a simplification of what we've been talking about previously. And so we have different formulas, of course, because we totally changed the mathematical constructs. So the root mean square distance is now equal to that n to the 1/2 value, where we have, as it says here, n steps. Each step is a segment of length b, times that value of b, Cune step versus whatever number of steps we have. And of course we could change this. As we change n and b together, then how well this approximates that overall length will change. Is that my phone doing that? What the heck? Does everyone see that? All right, it's just different approximations. And we can think about n, depending on the context, being equal to this value of the number of carbon-carbon bonds divided by the characteristic ratio. B then is equal to the characteristic ratio times L, which is that length again, 0.154, for the most part, meaning that we end up with a formula for the root mean square distance being equal to the quantity n c sub infinity to the 1/2 times L. So it gives us the same result in that context, but involves a different overall approach to getting to that result. All right, so I've thrown a bunch of stuff at you here, and the question is, what do you need to know? And basically what you'll need to be able to do is, if I give you the molecular weight of polymer and I give you C sub infinity, you should be familiar enough with the use of these formulas, and I'll give you homework that helps you get to that familiarity, to calculate the end-to-end length using these different quantitative approaches. Either the contour length, which is just high school geometry, freely jointed chain model, the free rotation chain model, the real chain model, and then finally the Cune segments model. Okay? And you're not familiar with that now, but by the time you work through it, it's quite straightforward. As long as you just keep the formulas straight in terms of which one applies to which situation, there shouldn't be any struggles here. So for example, if I give you a polyethylene with a molecular weight of 3 million, the carbon-carbon bond length is still 0.154 or 1.54 angstroms. And in this case, we choose that characteristic ratio to be 6.8. All right? And first off, very importantly, assume all trans conformation. What is the contour length of the chain where that's stretched completely out? And so you can go back to that other slide and crank through that number on your own. It's not very difficult at all, but just get used to working with these numbers. And that's what the homework is really all about. How do we work with the numbers? How do we represent the numbers? What units do we use? That's all very important so you can efficiently work through these problems. And then using the freely jointed chain model, what is the end-to-end length? So knowing n and knowing L, we'll be able to give you that root mean square distance. And then we also have the, free rotation chain model, which involves a different formula, a quantity 2n to the 1/2 times L. And then there's the real chain model. And again, it's all about recognizing these things. That value is going to be the quantity n c sub infinity to the 1/2 times L. And then we have the Cune segments model, which gives us the exact same formula in terms of being able to work out that distance. And so, but for the Cune segments model, I'll give you n and b. All right. So I'll give you other information that requires you to work through that. Okay. Any questions about that? Again, it's all very unfamiliar, but work through it, and you'll see how well that it's really pretty straightforward. Okay, so has everyone handed in their homework or emailed me their homework? Yes? All right. So no class on Wednesday, so I can grade this extra test that I now have to grade. All right, so I'll see you guys on Friday.
Yeah.
That is not correct, in case you saw it.
That is nice. I have a lab work to finish.
Okay. All right. Well, I'm definitely happy. That's not correct.